tool. That's okay. Beginning process. Okay, so if we rewrite this 60 polynomial in terms of some 5D invertible field theory by thinking about a domain or changing the setup, here. Yeah, it's basically thinking about 60 aligned polynomial with some domain wall jumping the setup from 0 to 2 pi. That domain wall has this 5D invertible field theory. And they also carry the same information for the anomaly, in the sense of the non-conservation of the baryon and lepton curve. Yeah. And in that case, this invertible field theory and anomaly capture the same information, and that's why people usually say this is the anomaly inflow. You can place the Sn on the boundary of this 5D invertible field if you want to. Any question? Okay. And the last claim we need is that once we break down the U1 or the P-line cell down to a discrete Z4, somehow the two of the Z class leveled by their quantum number here and some of the charge for the fermions, they'll break down the two of the Z class to a Z16. But in either case, in both cases actually, the index is related to this difference between the number of family and number of rank. So this will be a main player, an indicator for what standard model has suffered. Any question? Okay. So in the first part of my talk, or earlier motivated, I'm trying to cancel what has been suffered for the standard model by new suffers. And this is one interpretation. I like this interpretation maybe a bit more than the non-invertible symmetry, but seems like most people hasn't feel that way. But the reason I like it is because once you get this sector, you can try to construct them, and perhaps you can start to compute things to predict something. Even though this might be really hypothetical, but I really feel like this plays some role, and I have some reason for myself. And that's one way to go to interpret this phenomenon by cancelled by some new sectors. However, the second part of my talk, I will go a different route. Okay, so and I will mention that. Okay. And kind of to recap, the reason that we say that this anomaly can be cancelled can be start from thinking about something called anomaly matrix. Suppose I have an anomaly index from object flow from UV and flow to IR. There's a possibility the symmetry might be just broken, and you can match by symmetry breaking basis. And there's a possibility, so this will be this one. So anomaly index flow on the object flow. It's a preserving index, but the phase IR dynamics might be different. However, it's possible you can have a symmetry preserving phase to match the anomaly. Something called the symmetric gap phase without any low energy signature, but gapping by interaction is called symmetric match generation. This is not possible when the anomaly index is non-trivial. However, there are other possibilities I was mentioned that it can be symmetric gap T of T, and also the symmetric free fermion or symmetric with intelligency of T. And this is an anomaly inflow picture. However, if you try to flip the picture, thinking about that all the phases add up together, make the anomaly index be 0, then this is known as anomaly cancellations. Then what I was doing earlier was identify the anomaly index for the standard model and try to give them a meaning of their phases, the phase structure, and then try to aid possibility that beyond what we know in the Dino setup. And just also to mention that the anomaly cancellation can also go to one alpha dimension with invertible field theory. So this is all the cases. And let's see. Yeah. So this is, if you put in the standard model context, they are kind of city somewhere for certain basis. But what has been mainly used for canceling Z and anomaly were just the Marana, fermion, their methods. But what is new is this time, either the 5D bulk or 4D TQT or 4D CFT. So this is using different ways. Thinking about action might be more rich. Yeah. So that's it. And that's the picture. Okay. And then now let's go to the symmetry. I set up the anomaly, and I think I will just take that Z, the two of the this anomaly indexes, the what we need to use later. But now let me just say a few words about symmetry. In the modern way of doing the symmetry, is actually you can think there is some just colloquially, if we want to measure global symmetry, we need to find something which is measured doing the measurement, and that's called charge operator. And there's something else being measured. These are called a charge object. So U and O are respectively measured and being measured. And there's also terminology people say symmetry generator as charge operator as topological defects. These are somehow interchangeable. And the modern way of viewing symmetry generalize the notion not viewing the charge object as zero-dimensional object, but the charge object can be extended. Okay, suppose I forget about this thought, just for thinking about this as a point, as a charge object. Then it can be a fermion charge under fermentarity, and you can find a fermentarity operator living in some codimension 1 wrap around this. And you can change this Hamiltonian picture, see that this crossing of this fermion through this charge operator, you will gain a fermentarity base. In the space-time picture will be a link. So that's why the measurement is a charge operator link with charge object. I compute the path model. But in the generalized symmetry, include a p-form symmetry such that the charge object can be p-dimension, while charge object can be codimension p plus 1, which is just total space-time b minus p minus 1 dimension. Take a Wilson line as one form symmetry as example. The charge object is one dimension Wilson line. In 4D space-time, you can link this 1D Wilson line by 2-dimensional surface, such that they have a link number 1. And once you fill the 2-dimensional sphere with a 3-dimensional ball, they have 1 point intersecting point. Depends on how you want, but at least it has 1 intersecting point. If there's a link number. And compute the polygon function for that will be the measurement of the symmetry phase. So this is a modern way of doing symmetry. Any question? So later on, if we want to identify symmetry in the standard model, we should find operators corresponding to this type. Either finding a charge object or finding a charge operator and study their property and their dimensionality. And you will say this looks a bit boring, different from what I learned from textbooks. So let me just say, Northern theory tells us that you're familiar. If we have a continuous global symmetry labeled by some continuous alpha parameter, maybe the U1, there's some conservation variation of alpha if the conservation occur D of the particle of J 0. And the charge conservation usually means that I consider a spatial slice with a fixed time, integrate over this current J0 along the spatial slice, and it's conserved under time evolution. But this is only a particular fact, appropriate in the sense that appropriate for define a charge operator also as exponent of this Q charge, and you will find this Hamiltonian commune with this U operator, right? This is the familiar case. But because the underlying theory is Lorentz invariant, and you can rotate different way of choosing the surface that you integrate over, you can even consider a generic closed surface. In the case of a zero-point symmetry, we need to consider codimension 1 manifold that you integrate over. Earlier was doing the spatial slice, but you can take just some closed manifold somewhere, enclose it. And in the case of one-point symmetry, we can consider a codimension 1 for this 2D surface, and then this will be the surface operator. And because this current that define the star J define this charge operator, that star J is conserved. So if you small deform this U alpha, by Stokes theory, this U alpha deformation will not change the measurement of the path-level partition function insertion of this space. So hence, this operator is called a topological. That does not depend on the deformation. And however, we'll discuss a bit more in the case when the current J is not conserved. In particular, it depends on external background suffer from anomaly. But so far, anything above is just the rephrasing of the unit symmetry. So any question? Yeah. So then we just need to find such a charge operator like doing a measurement and a charge object that be measured. And yeah. And let me just also say one thing, maybe give some example in case later on it's more abstract. In the 40 U1 gauge theory, there's a Wilson pure U1 without fermions, let's say. There's a 1D Wilson line, and there's also dual line called the tuple line, followed by this relation. dA is the part of the U starting AN magnetic. They have a different quantized QE, QN charge, magnetic and electric charge. But there's a corresponding charge operator, star dA and star DAN. But just based on the relation of this, dual relations, you can also rewrite the star dA as DAN, star DAN is star DA. And you can show again this operator is topological, means that small deformations does not affect. And it's kind of obvious because D squared is equal to 0. And the deformation for that current will be conserved in the case of a pure U1. So there's a U1 electric one-phone symmetry with object charge operator display, which actually written to you. Yes.
You want to add as a conjugate.
But yeah, depends on what you mean by conjugate. But if I identify the Wilson line A, followed with the gauge field A, with the tuple line with the dual gauge field A, if you say these are dual.
Yes. So it's related to the dual symmetry.
Say again.
The dual symmetry of
Maybe you need to clarify afterward. I'm not sure what you mean. These are kind of too vague. So there's also something similar for the discrete ZN theory. Then in that case, the line that's one dimension, there's a surface, but the charge object and charge operator are somehow switched. Where the electric one-phone symmetry are made by the two-phone field, but that two-phone field is a charge object for the two-phone magnetic symmetry. And you can read the slide. But the main point is that modern formulations provides the necessary view to think something more general. But then with that context, we can write down the standard model symmetry, including the zero symmetry, that acts on the point particle, and also one symmetry acts on lines. And for the purpose of my talk, I'm not even going to talk about too much about one-phone symmetry, but I'm saying that this is actually known and studied in literature. We do know that even different standard model gauge group mass Q, they are different type of one-phone symmetry. Subtly depends on this Q. And they can be computed by the center of the gauge group or the Pontryagin dual of the Taiwan homotopy of this. But the point here is that the main point here is that one can analyze that symmetry carefully. But how can this be used? Once this is known, symmetry is known, let me say that you can really classify anomaly with respect to that symmetry. And that is basically the part when I was teaching some time ago, I tried to present this result, but I was building on knowing the symmetry already and classifying all the possible anomaly associated with that symmetry by classifying the symmetry invertible field theory in one high dimensions by Cobordism. But this data is meant to show that the Z class are the final graph type of anomaly, what is Zn, which is so-called torsion or finite group part, is none. And what has been playing a role today will just be the Z16 and two of the Z2. I hope it's Z2, Z2, yeah. But the main point is that this analysis is more or less complete. So there's a confidence, at least for me, to be confident that we don't miss much within the context of invertible symmetry. So this is kind of complete within this context. Okay, so this part I just skipped. I think I will not. So yeah, let me go to the non-invertible symmetry right now. So what we need in comparison with invertible symmetry is that invertible symmetry form a group law. And when you identify a charge operator, U labeled by some of the group element that label the symmetry, say alpha and G, then the charge operator has the similar behavior as the fusion rule that it has basically has a correspondence. But for the non-invertible symmetry, it's a bit more subtle, is that if we take just one simple example for the U1 or the subgroup of U1, which we will discuss, which actually will be rational angle subgroup of the U1. These are known as Q or Z of the U1. This Q Z element basically is part of Z, and we'll use that subgroup to construct something is non-invertible. That means that this charge operator labeled by this alpha within this Q Z, they have a fusion rule, not follow the usual group law, in the sense they do not have inverse. So that's basically precisely is that operators labeled by this element of this certain commutative monoid, which means without the inverse, and such that this non-invertible fusion rule corresponding to this monoids binary operations. And there's a surjective homomorphism from this this monoid M to Q Z. So this map is different from the previous ones, from group to group U1 to U1. But right now it's a monoid M to the subgroup of U1 Q Z. Okay. Yes. Yeah. Let me tell you. I hope I can talk about this. So if you heard something called IC, either in the 2D CFT or 3D TFT, they do have a non-invertible symmetry. And even just before go to formality, let's just consider some system like a condensed matter-like system, which is called chiral P-weight, a superconductor. That means the electron are paired not through the S-weight, but P-weight. And you can find out the vortices starting in this P-weight, chiral P-weight superconductor. It's Px plus IPy pairing. The vortex will trap some kind of a zero modes, and they behave like Marana zero modes. In the 0 plus 1 is a Marana zero, not Marana fermion in 0 plus 1, which is Marana zero modes. And if you fuse these two of these vortices that traps the zero modes, you will find out, you know, this Marana is sigma, which behaves, turn out to be like anion. Fuse these two will give you two states. One is bosonic, and one is fermionic. For someone who don't know field theory, you just need to know the state fuse two of the sigma anions. The energy spectrum will split to a bosonic sector and fermionic sector with two ground states. And this is the physical meaning for this fusion rule, sigma and sigma is 1 plus psi. Is this part clear? So there's a kind of a simple way to explain the nature of the non-invertible symmetry by identifying the, in this case, the charge operator. That charge operator turned out to be the vortices trapped in Marana zero modes at core. And then if you fuse them, there's a fusion rule like this. And the fusion rule will split the ground state to two sectors. One is bosonic, one is fermionic, which means one of them has charge 1 under fermentarity. The other one is charge plus 1. And the splitting of this ground state is the signature that the fusion of the charge operator gives rise to this fusion rule, which is not invertible. In the sense that you cannot find just one of the operator within the IC TQFT, let's say, such that sigma fused with something else will just give identity, but you will split. And that's also related to the fact the sigma anion has quantum dimension square root 2. Anyway, and as fusing them will give total quantum dimension 2 for this system. Okay. So this is the kind of symmetry we want to identify in the standard model of this type. I think this part we just skipped. There's a slide you can read. And let me see. So this part is the work actually done last year. Some of you possibly already heard several times about this. What I did is saying that looking at the QED with fermions and with U1 vector gauge symmetry and with U1 actual global symmetry. We know from other Jacqueline which says that the actual current is not conserved, and it's up to this F/F for the vector side. So these are the mixed anomaly between A and the vector, actual and vector. Basically, this diagram. And because if the V is only a global, vector is a global symmetry, A is also global, this will be just topological, it's fine. It's just a signature of the theory, it's not a sickness. But if V is gauged, then the actual current is not conserved. This is the known story. And the story happened last year saying that, however, they try to make sense of this formula in the sense that this formula says the actual current for the Hodge field of this JA cannot build a topological operator because it's not conserved. I explained earlier. But if I try to move this right-hand side along, you might say, perhaps I can consider the exponentiation of this operator and make it a topological operator. Okay. I should mention a few things that later on we will turn on the gravitational background, so I will skip some of the matrix dependence in the notation, but these are implicitly in the differential form, just let you know. Okay, so let's go back to this part. So this charge operator, if you naively write this way, here, yeah. So the first statement is that if you just stop on this, the current that's up from integer anomaly and try to think about what is topological by deformant, then there's a Stokes theorem tells us that deform from M to M prime, you need to integrate over, and the non-conservation of that current can be filled to this one natural dimension bounded by this for the surfaces. Suppose that on this surface are bounded by this boundary with this two manifold. Then he says that these deformations thus depends on the path and also the integration within this extra dimensional N, right? But earlier the statement is that suppose we move this A wedge here onto the left hand side, and then what happened is that we still use the alpha as the U1 angle, and naively it looks like this will be just 1. And this looks topological, but as some of you might know that this is not really gauge invariant under large gauge transformations, because 1/4 pi ADA can up to some vector can jump by phase by 2 pi times z. So unless alpha is quantized appropriately, not within the full U1, then this may not make sense. So what the recipe they did is that suppose I only look at the rational angle 1/n of that the U1 alpha, then you can regard this alpha taking alpha taking value 2 pi over n. So take alpha as 2 pi over n. And then there's a tricks in condensed matter or also in field theory known that you can integrate out dynamic field of A with level n, which are known as U1n. Chern-Simons theory described by finite fraction 1/n quantum Hall states, and integral this will give rise to the background field of this A. So what happened is that the original this big A formulation of the Chern-Simons is not gauge invariant on the large gauge transformation, but the small A formulation does, and this also maintains the same topological property for the deformations. So these will be a good operators. However, the outcome is that the fusion of this operator, you cannot find the inverse. You can find the permission conjugate of the operator, but they will not give rise to just the identity element, which means these are not quite invertible. And these are not quite unitary in the sense that the permission conjugate of that operator also does not give identity. So any question? Yeah, these are kind of dense, but the summary of that part is saying that you can find the original operator suffer from ABG anomaly is not topological by scale invariant. The modified one just by naively changing the J current by shifting by this background A field. is actually topological, but not gauge invariant of the large gauge functions. But you can rewrite this as this type. And this will be gauge invariant topological, but not quite invertible.
3 minutes.
Yeah, okay. Yeah. So let's go to the reinterpretation of the standard model now. It's similar, just say the current of the B minus L type or Q minus NCL is actually anomalous. So we can try to ask if we keep this version of standard model without adding sterile neutrino, without adding the new BSN sector that I proposed in part 1, then the standard model suffers this anomaly. And it will break the continuous U1 B minus L if we turn on this gravitational field. And this part I need to clarify because gravitational field might be background or dynamical with small perturbations or the full quantum gravity. And this 3 different version has slightly different outcome. We'll discuss that in detail. And however, let's just look at the formula for this current non-conservation for B minus L is similar. One is this related to this FHF from the B minus L current, B minus L gauge field itself. Another is related to this weight from the geometry. So yeah, the clarification is here. Suppose I turn on background gravity. We may not say the U1 symmetry is broken, the invertible U1 symmetry. We may just say this is just anomalous, total anomaly, basically. And we can still construct such a non-invertible symmetry defects, and I'll show you. But I think the interesting part is something like semi-classical, not quite like background, but semi-classical fluctuation around a fixed background. And such that we can really think the symmetric fluctuation will break the invertible symmetry purely just by gravitational anomaly. And we can still consider the topological defects come from out here. Okay. And now this we will not, however, our context of the constructing this non-invertible symmetry will not really apply to the full quantum gravity. Not only because the U1 invertible symmetry part is already broken, but also the non-invertible symmetry will construct is part of also the symmetry that you might call global symmetry for the system. But as we know, the quantum gravity for the full quantum gravity, we don't really have the global symmetry. So either this one needs to be broken or need to be dynamically changed. So this will be different type of consideration of gravity. I think the most useful will be consider this, but we can comment about this once we construct this topology. Question. Yeah.
Okay, it's 4 p.m. So.
Yeah. But I saw that we start a bit late.
What?
We start a bit late.
What's
the situation?
Well, you can go for another 5 minutes.
Okay.
I guess we can start 5 minutes later.
Yes. So let me just summarize my, what we need to do is actually very simple. I guess 1 minute is saying that if we start from the naive charge operator built on here without appending any this trace on which are termed, this operator basically stay not topological. Well, based on Stokes theory, it tells us that deformation depends on what is being deformed and filled by this which are termed. And these are the 3 manifolds that measure the zero form invertible symmetry, and these are the deformation paths. However, by Stokes theorem, we can rewrite this as the derivative of gravitational Chern-Simons term. Okay. So based on the similar tricks, if we move the right-hand side to the left-hand side, then you will see that this operator becomes topological. That deformation now, go from here to here does not depend on this path because we just redefine the operator. But there's a similar issue, just like the previous case of the ADJ anomaly of the U1B and U1A. In this case, once the gravitational field start to fluctuate and you consider the large gauge formations, this gravitational Chern-Simons can shift 2 pi vectors, and we would like to fix that. Okay, and the way even before we do that, actually there's another thing we can comment is that actually this whole terms gravitational Chern-Simons term thus has the framing dependence. That means that under the change of this field bind, you can actually get a phase proportional to the chiral central charge, and that's so-called the framing anomaly. And that means that this theory, by its own is not quite framing anomaly free. However, we can decorate or aid this term by 3D TQLT by its own dimensions. And these are some version of TQLT known Witten-RT type of TQLT. Given any rational chiral central charge C, there's a way to cancel this framing anomaly, such that the operator construct from the U tilde and the TQLT, they have a framing anomaly free. And then the condition will just be matching the chiral central charge C and matching the phase alpha that you take some rational angle and matching this coefficient K that's written from the anomaly, particle physics anomaly data from this K, which is read from this. Okay, so let me summarize by showing the table. There are steps. The step is similar to what has been constructed with ABJ anomaly, except that we are changing the background ADA type term to a gravitational Chern-Simons and with level K. And the alpha angle now not just being U1, but need to restrict to a rational angle. Okay, and this rational angle carry the information to match the central charge and the anomaly index data K. And once you have that, this more or less done for the gravitational anomaly. But because this U1 B- cell also suffer from the cell anomaly, so there's an additional subtlety to aid additional aberrating Chern-Simons term to cancel that. So these four steps together will be able to do just column by column. In the end, you'll be able to construct a topological gauge invariant on the coordinate of field bind transformations, such as framing anomaly free, and it's also a U1 gauge invariant under the B- cell transformation. And this, however, will not be unitary and invertible, just like the previous case. So this will be the operator that identifying non-invertible symmetry of this type of anomaly. But the reason for this non-invertible symmetry operator is more or less enough to show categorical symmetry description for standard model is because for the standard model, we do mainly have two types of anomaly, as I kind of indicates, within the minimum standard model context. So there's a two type of this anomaly. So I think I'm sorry I'll skip this two slides for this technical explanation for detail, but the main part is that because we in the first part of the talk I mentioned that only the Z-square type of local anomaly will present when you have U1 B- L and discrete Z4 X symmetry give the Z-sigma anomaly. So if we identify the interpretation of the non-invertible symmetry operator of this sort of this anomaly that breaks the invertible symmetry, then basically this already gives some essential part of the thing we need to find for the standard model for the non-invertible symmetry. And in the first part of the talk, I require the kind of cancellation of anomaly by aiding in sectors and possibly go to higher dimensions. But in the second part of the talk, that's not what I do. Basically, I'm trying to look at the symmetry operator in a different way by reconstructing the symmetry operator. In that case, we keep the anomaly, the original anomaly, but solving partly that anomaly even into define the operators, the non-invertible symmetry operators. And so this is kind of a picture of what's going on to this interpretation. And I didn't have time, but there's a similar analogy when we change the Z class, particularly local anomaly, to the Z16 class anomaly. And one can also control the defects, symmetry defects. Yeah, so I guess that's more or less it. Yeah, so in the invertible U1 symmetry may suffer from the mixed gravitational anomaly under certain gravitational background, such as gravitational instanton. These are analogous to the ABJ anomaly, but change ABJ anomaly to gravitational background. But certain non-invertible symmetry counterpart of this discrete subgroup U1 actually can be refined, and you can define the non-invertible symmetry. In my talk, I only focus on writing down the symmetry operator, the Chern operator. But there's possibly more things to be done. And there are other models who consider something related to standard model, but I think for the context of the standard model particle, I think this construction is kind of minimum. The only thing that is used for throw away is the sterile neutrino, and which is not really in the standard model. So that's kind of minimum. And because no global symmetry in quantum gravity, once we construct these defects, there should be some hint on how to break this symmetry, non-invertible symmetry, and how to gauge it. And there should be some interpretation of this leptogenesis, baryon-genesis, if you care this gravitational anomaly. There could be something different to say if we change the Raman mass, the sterile neutrino to this highly entangled TQRDC sector. Yeah.
Any questions? Well, let's give another round of applause to our speaker. Okay, I will